Let us discuss the conformation analysis of cyclohexane. Cyclohexane is the most studied cycloalkanes. Among all the cycloalkanes, the conformational analysis of cyclohexane is done very well, or in an elaborate manner. And its conformational analysis is quite interesting too. Now, usually when we write this cyclohexane, we write it in the planar form, isn't it? Like a hexagon. Now, this is usually the way we write cyclohexane. Now, when we write the structure of cyclohexane like this, the bond angle will be 120 degree for the this planar structure. Okay. But we know that in cyclohexane, the carbon atoms, all the carbon atoms are sp3 hybridized. Okay, and hence the bond angle must be 109.5 degree or 109.28 minutes. Isn't it? That's the ideal bond angle for a tetrahedral atom. And when the atom attains sp3 hybridization, or is of atom is sp3 hybridized, then automatically it will have a tetrahedral structure. And the expected bond angle for sp3 hybridized system is 109.5 degree. So if we write cyclohexane in the planar form, the bond angle will be 120 degree, which is quite more than, or very much more than the expected bond angle or the actual bond angle for a tetrahedral structure. So there will be some sort of angular strain when we write the structure of cyclohexane in the planar form, or if the cyclohexane exists in the planar form. Moreover, there will be a torsional strain because the CH bonds on cyclohexane will be in the eclipse form if we write or if the cyclohexane has got a planar structure. Alright, so if the cyclohexane is having a planar structure, there will be angular strain and torsional strain. So in order to avoid this strain, the angular strain and torsional strain, cyclohexane adopts a puckered structure. Okay, by puckered structure means a deformed or what you can say is a deformed structure, or a distorted, that's more better word to use, a distorted structure. Okay, there will be a distortion happening on the planar cyclohexane. So cyclohexane will not exist in the planar form, but rather it will be in the distorted form or in the puckered structure. Now let us see which are the or how the puckering happens. Now if this is the cyclohexane ring, the planar ring, now puckering can happen when one carbon is pulled down and the other carbon is pulled up. Okay, so that means that the opposite carbons, okay, the opposite carbons, among the opposite carbons, one is pulled down and one is pulled up. So we can say that if we number the carbon atoms from here, 1, 2, 3, 4, 5, 6, carbon 1 is pulled up and carbon 4 is pulled down. Then we get a structure like this, which is called the chair form. Another possibility is both the carbon 1 and carbon 4 are pulled up. Okay, then we get a boat form. Another possibility of puckering is that only one carbon atom, that is either any one of the carbon atom, is pulled up. Then that is called the half chair form. And then we also have a twist boat form, which is between a structure between the chair and boat, and when we convert the one chair to another chair, we go through boat and twist boat, etc. Here, almost all the carbon atoms are displaced from its original plane. So these are the various conformations of cyclohexane. We call this chair conformation, boat conformation, half chair conformation, twist boat conformation, etc. Now let us see how does this puckering happen. That is, how is that the chair form is formed or board form is formed. Now remember, the cyclohexane will undergo this change from chair to board to half chair, chair to half chair. All these conformations are formed during this puckering, or there will be interconversion of these conformations. There will be interconversion of these conformations of cyclohexane. Okay, let us see how that interconversion is happening. To explain the interconversion, I am taking the help of a video from YouTube. Now I'll just run this video. You can see here. See, this is the chair form. Now it's slowly changing, and you can see the half chair form, and then twist board, and then it forms the half chair again, and then chair form again. Alright, now once more you can view this. See, you have the chair form here. This is chair form. Okay. Now you see, this is moving up, this chair, the right hand carbon is coming up. It has become a board form, twist board, and then the left side carbon has come down. You get another chair. Okay, once more. Half chair, twist board, twist board, half chair, chair. So that is how the rotation or the interconversion happens. Okay, it starts with a chair. Alright, once more let's see. Let's have a chair here. Yeah, this is chair form. Okay, start with chair, then goes to half chair, then to twist board, then to board, again twist board, half chair, and then chair. So that's the cycle, or that's the route which the molecule or cyclohexane takes to have the interconversion, chair to chair. We call it as chair to chair interconversion. This interconversion of the various conformations of the cyclohexane is called ring flipping. We shall discuss ring flipping in detail later. We also need to discuss about the energy aspects or the stability aspects of these conformations. Now we shall discuss those. Before we discuss the stability factors, etc., we need to know how do we draw the most stable conformation of the cyclohexane, that is a chair form, and how does the bond appear, etc. The alignment or the orientation of the bonds, etc., are important. This is very much needed in order to explain ring flipping, the stability factors, etc. Let us see how do we draw the chair conformation. Now, this is how the chair conformation appears. We have both the 3D model and the what is called the 2D model, two-dimensionally what we have drawn here. Now what you see here is when you draw the chair conformation, you draw the carbon 1, carbon 2, carbon 5, carbon 4 bond parallel to each other. Okay, so we have numbered the carbon 1, 2, 3, 4, 5, 6. The C1, C2 bond must be parallel to C4, C5 bond. The C2, C3 bond must be parallel to the C5, C6 bond. And the C1, C6 bond must be parallel to the C3, C4 bond. Okay, so this parallel nature of the bond is to be maintained. Okay, so this is how we draw the chair form of cyclohexane. Now here you can see here, this is the chair form. Now when you observe the either the three-dimensional structure or the 2D model, you find that carbon 1, carbon 3 and carbon 5. So you have carbon 1, carbon 3 and carbon 5. These three are a bit up, lifted up, sort of lifted up. Now they are called the up carbons. Now these 3 carbons fall in a single plane. Okay, so carbon 1, carbon 3 and carbon 5 fall in the same plane. They are lifted up. They are called the up carbons. Now carbon 2, carbon 6 and carbon 4. We have it in the 3D model. Carbon 2, carbon 4, carbon 6. Carbon 2, carbon 4, carbon 6. These 3 carbon lie below, a bit below. They are pulled down and they fall in the same plane, coplanar, 2, 6 and 5. Okay, so 1, 3 and 5 are coplanar, carbon 2, 4 and 6 are coplanar. And these 2 planes are parallel to each other again. Okay, so remember, while drawing the structure of the chair conformation, you must draw carbon 1, C1, C2 bond parallel to C4, C5 bond, C2, C3 bond parallel to C6, C5 bond, and C1, C6 bond parallel to C3, C4 bond. And remember, carbon 1, carbon 5 and carbon 3 and carbon 5 are pulled up and they are a bit, they are coplanar. Similarly, carbon 2, carbon 4 and carbon 6 are coplanar and they are pulled down, a bit down the plane. Alright, now we'll see how do we draw the CH bonds on the chair form. Now we have the structure here. Now see here, the red lines, they represent the CH bond. Now you can see here, the bond, CH bond on carbon 5, CH bond on carbon 1, CH bond on carbon 3 are drawn upwards. So those carbon which are pulled up, there one of the CH bond is drawn upwards. And the carbons which are pulled down while puckering, the carbon 6, carbon 2 and carbon 4, their CH bond is drawn downwards. Okay, that's how you draw. And these bonds are called axial bonds. Okay, which are literally perpendicular to the plane, or you can say they are parallel to the axis. If you will be having an axis of symmetry here, and these bonds are parallel to the axis of symmetry. In fact, it is C3 axis of symmetry. So that is the axial bond. So since the bond is parallel to the axis of symmetry, C3 axis of symmetry, they are coaxial to the C3 axis of symmetry, hence they are called axial bond. Now, the other bond, we have answered to the 3 valency of carbon, one mode is there. The other CH bond, this one here over here, is drawn like this. Now here you can see carbon 5 is pulled up. One of the bond on carbon 5 is pointing upwards. Now the other bond is pointing downwards, slow, a bit tilted downwards. You can see here. Okay. Now on carbon 6 you must have a similar bond. Okay, now that will, here I have put the carbon 1 here. See, carbon 1 is also, the CH bond is up, one CH bond is up, the other CH bond will be a bit downwards. See, you can see here, slanting. Okay, see, similarly on carbon 3 it is downwards. So the axial bonds on the up carbons are pointing upwards. Now these blue bonds, they are called equatorial bonds because they are almost, if you draw a circle around this molecule, these will be on the equatorial line. Okay, so these blue bonds are called equatorial bonds. So the equatorial bonds on the up carbons are pointing downwards. Now the equatorial bond on the carbon which is pulled down while puckering is pointing upwards. See, on carbon 6 it is pointing upwards. Now carbon 2 also it is pointing slightly upwards, similarly on carbon 4. Okay, so that you must remember. So these are called the equatorial bond. One more thing, the equatorial CH bond on carbon 5 is parallel to the C3-C4 bond. Okay, equatorial CH bond on carbon 5 must be parallel to C3-C4 bond. Equatorial CH bond on carbon 6 must be parallel to C1-C2 bond. Equatorial CH bond on carbon 1 must be parallel to C2-C3 bond. Equatorial CH bond on carbon 2 must be parallel to C1-C6 bond. Equatorial CH bond on carbon 3 must be parallel to C5-C4 bond. Alright, so the equatorial bonds are parallel to the CC bonds, while the axial bonds are coplanar to the C3 axis of symmetry. Okay, so while drawing the structure, you must maintain that parallel nature. That's important. Okay, usually we find a clumsy appearance over these on carbon 6 and carbon 3. Sometimes it will be falling along with the CC bond. Okay, so you must be careful while drawing it. If you practice once, twice or thrice, it will be easy for you. Alright, so this is how we draw the what we call the chair conformation of cyclohexane. Hope this is clear to you. Now, these bonds which are above the plane, so there is this axial bond is above the plane, the equatorial bond on C6 is above the plane, again the axial bond on C1 is above the plane, the equatorial bond on C2 is above the plane, axial on C3 is above the plane, axial on C4 is, equatorial on C4 is above the plane. Now these bonds are called beta bonds. Okay, they are not named as beta. Okay, that's the nomenclature given to it. We need this, this concept must also be clear. The bond which is above the plane is called beta, and the bond which is pointing below the plane is called alpha. Alright, so we have the alpha bond here. See, C equatorial CH of C5, axial CH of C6, equatorial CH of C1, axial CH of C2, equatorial CH of C3, axial CH of C4. They are pointing downwards. Okay, so they are called alpha. Okay, their nomenclature is alpha. So that is the nomenclature and the way we draw the various bonds, CH bonds, and the parallel nature of CC bond and CH bond you must take care of. Alright. Now, the distance between any two adjacent axial bonds will be 251 picometer. Actually, I need to have axial hydrogen. Now, we'll be having hydrogen atoms on these axial bonds. The distance between these two hydrogen atoms will be 251 picometer. Okay, any adjacent axial bonds you take. Okay, up and down, up and up, etc. And the distance between any two equatorial bonds will be, or hydrogen will be 249 picometer. Okay, so the distance between two adjacent up and up axial bond will be 251 picometer. The distance between two adjacent equatorial bond will be 249 picometer. The distance between an equatorial and an axial hydrogen will be again 249 picometer. Okay, so in chair conformation, the distance between the two hydrogen atoms on the adjacent carbon atoms or on the carbon atoms which lie on the same plane is much more than the 240 picometer, which is the distance distance between the nuclei of hydrogen atoms when they are put together. Okay, when they are placed one near the other. So when it is 251 or above 240 picometer, then there will not be any repulsion or van der Waals repulsion. So in a chair conformation, the distance between the different pairs of adjacent hydrogens are much above 240 picometer. Okay, or we can say it is much above twice the van der Waals radius of hydrogen. So the radius of hydrogen is 120 picometer. When you put two hydrogens side by side, and when we measure the distance from one nucleus to the other nucleus, it will be then 240 picometer. Okay, that is when we place them near to each other. Okay, just touching them. Okay, but here we have 251 and 249. So the distance, there is some distance between the two hydrogen atoms. So there we'll not, this compound or this conformation will not experience the van der Waals radius, van der Waals interaction or van der Waals repulsion, since the distance between any two pairs of adjacent hydrogen atoms is above 240 picometer. Alright, so that aspect you must remember. There are few more aspects regarding the reasons for the stability of the chair conformation of cyclohexane. Now, one thing is that the bonds are staggered. The CH bonds are all staggered, and then the distance between the hydrogen atoms, adjacent hydrogen atoms, is more than 240 picometer. Okay. Now, a few more reasons which we can just list down the stabilizing factors of chair conformation. Okay, it is considered to be the strain-free conformation. Cyclohexane, in fact, is considered to be the strain-free cyclic alkane, and the reason is because of this chair conformation. Okay, and since the hydrogen atoms are in the CH bonds are in fully staggered form, there will not be any torsional strain. So we can eliminate the torsional strain is eliminated. And then the bond angle, the angle strain, if we have seen in the beginning, if the cyclohexane was in the planar form, the bond angle would have been 120 degree, but that is not the bond angle for an sp3 hybridized carbon. For the sp3 hybridized carbon, the ideal bond angle is 109 degree 28 minutes. Now in the chair conformation of cyclohexane, the bond angle is 111 degree 5 minutes, which is almost near to the sp3 tetrahedral bond angle. And this slight increase in the bond angle of chair conformation from the tetrahedral bond angle, in fact, is a stabilizing factor. Now, when this slight increase in bond angle flattens the conformation, and this flattening will balance the angle strain and torsional strain, will bring a balance between the angle strain and torsional strain, thereby minimizing the energy of the system or minimizing the energy of the chair conformation. Okay, so these are only a few aspects we need to know. There are more aspects more stabilizing factors. We shall discuss those in detail later. Now we need to discuss one more conformation in the structure of one more conformation of cyclohexane, and that is the Bott conformation. Alright, now Bott conformation is formed during this ring flipping from one chair form to other chair form. To explain the structure of the Bott conformation, I am taking the help of the website ChemTube 3D, wherein we get the molecules in their three-dimensional form, and we can even flip or spin or rotate the molecule. Now let us take up this is how the ball and stick model of Bott conformation appears. Now this was our chair conformation, right? You have the 3 carbon atoms on top and 3 carbon atoms at the bottom, up carbon atom and bottom carbon atom. Now this on flipping gets converted to the boat conformation. Now, if we put it into the stick model, and this is more clear. Now, the boat conformation, can see here the axial bond, which was, these bonds which are pointing downwards, these were actually axial in the chair conformation also. They're not actually parallel to the axis. There is a axis over here. Now these bonds are not parallel to the axis. They're a bit bent, right? You can see the bend here. Alright. So these bonds which are pointing downwards are called the axial. There are 4 axial bonds. You can see when we rotate the boat here, 1, 2, 3, 4. They're called the axial bonds. Alright. And then these bonds, these two which are pointing towards us, and this bond and this bond which is pointing away from us, they are the equatorial bond. They're called the equatorial bond. And this bond, this bond on this carbon and this bond on this carbon, this CH bond are called the flat pole bonds, or flat poles. Okay, these bonds which are straight, they're called the linear bonds, linear CH bond. Okay, so this is how the boat conformation appears. Alright, so you can see here these axial and equatorial bonds are eclipsing, right? Alright, this is the way the boat conformation appears. Alright, now let us see how we can draw that, and then we shall explain it much more in detail. So this is the boat conformation. We shall see how it is drawn. This is how we draw the boat conformation. So you can see the axial bonds. The blue bonds are the axial bonds, axial CH bonds. The black bonds are the equatorial CH bonds, or the dark brown bonds, or the equatorial CH bonds. Okay, now the axial bonds, all the axial bonds eclipse each other. All the equatorial bonds, the equatorial bonds eclipse each other. And the green bond, CH bond, is called the linear bond, which is almost 180 degree apart. Okay, they're not going to interact at all. And then we have the flat pole bonds. Okay, flat pole CH. Now this flat pole CH, the distance between two flat pole CH is 183 picometer. Now this distance, that is the 183 picometer, is less than twice the van der Waals radius of hydrogen. Van der Waals radius of hydrogen is 120 picometer. So when we place two hydrogen atoms near to each other, just touching each other, when we measure the distance from one nucleus to the other nucleus, it will be 240 picometer. So 240 picometer is the minimum distance wherein there is no overlapping of the hydrogen atoms. Now here we have the bond distance, the distance between the flat pole hydrogen as 183 picometer, which is less than the 240 picometer. So obviously these two hydrogens will be interacting, or they will be overlapping. So we will, the boat conformation will experience a repulsive force, van der Waals repulsive force, and this repulsion interaction is called flat pole interaction. And because of this flat pole interaction, boat conformation or boat form is less stable than the chair form of cyclohexane. There are, of course, other factors too. We shall discuss those. Alright, so one of the reason why boat conformer or boat form is less stable than the chair form is the flat pole interaction. So hope it is clear to you as to how to draw the chair form of cyclohexane and boat form of cyclohexane, and how we must place the bonds, the CH bonds, on these two forms. Now next we shall be discussing about the energy aspects of the various conformations and also the ring flipping. Do write the structures and make yourself, practice drawing these structures so that you can draw neat structures, okay, without any overlapping of the bonds. All right. Thank you so much.